Welcome to another podcast. This episode we're going to be taking a look at how to perform implicit differentiation. Now, the word implicit and explicit is often used to describe how we can write out a function in terms of solving for the dependent variable or not being able to solve for the dependent variable. And so I wanted to take a second to talk about that distinction. The idea is normally the functions that we've worked with are of the form y equal f of x, where y is the dependent variable and x is the independent variable. If we can write the function in that form, then we say that y is determined explicitly in terms of x. One example of this would be just the line y equal 3x minus 2. You always called this the slope form of the line. So in algebra in high school, you would have called it the slope-intercept form of the line. But mathematically, it's just really the explicit form of the line. On the other hand, if we wrote a line of the form f of xy equal usually some constant c, then we call that an implicit representation of the curve. And just looking at the one we have here, it would be something like y plus 3x equal negative 2. That would be the implicit way of writing this line. And in high school, you would have called this the standard form of a line. So there's really not much difference between the two for something like a line. It's really just an algebraic manipulation to get you from the explicit form to the implicit form. However, when you deal with something like a circle, so remember what a circle looks like. So circle of radius 1 centered at 0, 0, for example. So if we have a circle of radius 1 centered at the origin, then the equation of that line is x squared plus y squared equals the radius squared, which in this case is 1. This is an implicit description of that curve. If I wanted to solve for y, then we could solve for y as the square root of 1 minus x squared, but remember it's plus or minus that. And so the plus is the top half of the curve, and the negative is the bottom half of the curve. So it's the top semicircle versus the bottom semicircle. And the problem with this is not a function. And the reason it's not a function is you can see here, because of the plus or minus, for each value of x, you're going to get two values of y. And that's, by definition, that violates the vertical line test, or the definition that we have for what constitutes a function. So the idea here is that these implicitly defined things, these implicitly defined curves, and I'm going to call them curves from now on, these may not be a function. So we've dealt with parametric curves already this semester, and some parametric curves are not functions, just like some implicitly defined curves are not going to be functions. Because of that, we may have some things go haywire on us, like if we try to find a tangent line at a point, we may get two tangent lines at a point. But for the most part, being able to perform implicit differentiation is reliant on our ability to do chain rule and understand that when we write it in the form y plus 3x minus 2, that y here is in fact a function of x. So let's just go ahead and try to find the tangent line to the curve, or the slope of the curve on a circle. So the question I have here is, what is the slope of the curve x squared plus y squared equal 1? Meaning, at any point on the circle, what is the slope at that point? So basically I'm finding a formula for the tangent line at any point of a circle. Well, the way that you do this is you suppose that y is a function of x, which it is. We solved for it here. So here you can see that y is a function of x. It just happens to be two different functions of x. And the first thing that you do is you want to take the derivative of both sides of the curve. So I'm going to take the derivative with respect to x of this implicitly defined function by taking the derivative of both sides to start with. So the derivative of x squared plus the derivative with respect to x of y squared equals the derivative with respect to x of 1. So I'm basically distributing the derivative using the linearity property. Alright, so going from there, the derivative with respect to x of x squared, we know by power rule that's just 2x. And on the right-hand side, we know the derivative with respect to x of 1 is 0. But the question is, what do we make of the derivative with respect to x of y squared? Now, you might be tempted because you don't see an x to say that it's 0. But recall that y is a function of x. In fact, when I'm differentiating y squared, it's like I'm differentiating 1 minus x squared. So how do we represent that? The easiest way to do it is to go ahead and take the derivative of y squared with respect to x, which would be 2y, and then acknowledge that because y, the inner function, is a function of x, I have to do chain rule on it as well. So 2y dy dx, this is the implicit part of the differentiation. And all it really is it's an application of chain rule because my inner function, so the inner function here, y equal y of x, is a function of x. So the next step in this process is to try and solve for dy dx. And if I do that, then 2y times dy dx equals negative 2x, just algebraically moving it over. And I can arrive at an equation, which we call a differential equation, of the form dy dx equal negative 2x over 2y. And this is a decent enough stopping place because at any point x, y, I'd be able to tell you what the slope is. So for example, we know if we're looking at a circle, then the idea is we know specific points on a circle and kind of what goes on with them. So if I think about this circle here and think about, let's say, the tangent lines to the circle at important points. For example, right here, the tangent lines are horizontal on both the top and the bottom. So what are the values of those points? Well, both of these points correspond to x equal to 0. So you can clearly see that when x is equal to 0, dy dx equals 0 at the points where x is equal to 0. So that gives us the horizontal tangent lines, and we could also similarly look at the vertical tangent lines. The vertical tangent lines occur at the points where y is 0. So each of these lines correspond to y being 0. Because remember, it's centered at 0, 0, so here's the axis. And so at y equal to 0, you can see that dy dx is undefined, so I should get an undefined or vertical tangent at those points. And then at all the other points, I would just simply plug in the x and the y values to be able to find the derivatives at those points. And so the easiest thing we have is just to say that dy dx equals, canceling the 2's here, it would equal negative x over y. But I really don't want to leave it there. That's not as satisfying as having an answer that's only in terms of x. And so recall that I had y written as a function of x right here. So I can just plug in dy dx equals negative x over, I can choose either the plus or the minus. I'm going to choose the negative here so I can cancel the negative that's in the top. And so in doing so, we get this as our equation. So the idea is that the slope of the tangent line, or the derivative of the curve, is given by this formula. Or, had I chosen the positive one, I could have negative x over the square root of 1 minus x squared. Either of those would be formulas for the derivative or the slope of the curve for a circle of radius 1. So the first thing you see is that because it's not a function, one of the things we lose is we might not have a uniquely defined slope at every point. In fact, some points may have two slopes depending on maybe the direction in which they're traversed, or a host of other things that could go wrong with implicitly defined as well as parametrically defined equations. And so we're going to talk about some of those special cases in class. I'm not going to put them in the videos because they really are just special cases. But we're going to see that there are some things that happen with implicitly defined functions and taking their derivatives that don't necessarily happen with nice explicitly defined functions that we've been used to. Let's do another example of this. So I want to take a look at another implicit derivative here and just kind of walk you through the points and make sure that we understand them. So let's start with, I want to calculate dy dx for the function 4 cosine of x times sine of y equal to 4. So what would the implicit derivative of this look like? So notice it's of the right form. It's of the form f of xy equal to 4. So it is implicitly defined because it's f of xy equal to a function of c, or equal to a constant c, excuse me. So the first step is always to take the derivative of both sides. Now I'm going to make a small change here in that I'm going to go ahead and divide by 4 before I do that. So you can algebraically manipulate it before you take the derivative. So dividing 4 on both sides, I'm basically looking at cosine x times sine y equal 1. And if I take the derivative of both sides, then regarding y as a function of x, these are two functions of x that are multiplied together, so I have to do product rule on the left-hand side. So doing product rule, I have the derivative of the first times the second plus the first times the derivative of second. Now here's where the implicit differentiation comes. I'm taking the derivative of sine y with respect to x, where y is a function of x. And so the derivative of sine is cosine, but because I took the derivative here and y is a function of x, then I have to also multiply by the derivative of y with respect to x. And then on the right-hand side, the derivative of 1 is just 0. So if I have everything going correctly, then at this point I'm looking to solve for dy dx. That's the final step here. So that's going to occur algebraically. In this case, I'm going to add this term over. And so algebraically, this is equivalent to cosine x cosine y dy dx equals sine x sine y. And solving for dy dx is as simple as dividing sine x and sine y by cosine x and cosine y. And what you observe at this point is sine x over cosine x is tangent x, and sine y over cosine y is tangent y. Now, I would really like to do what I did up here, and that is write the derivative dy dx in terms of only x. And so if you'll allow me to make a little bit more room here, I want to go ahead and finish out that last piece. What we basically have at this point is we have a tangent of y, and we would like to substitute something in for y. So I've got to come back to my original problem. Can I write what's implicit? Can I write it explicitly? So if I do that, what I'm basically trying to do is I'm trying to express f of xy explicitly so that I can plug it in for dy dx. Well, this can't always be done, so keep in mind that what I'm about to do I can do for this problem, but I can't in general always do this. And you're going to see this in the second video, the follow-up to this, that we can't always do this third step. Some problems can only be expressed implicitly. You cannot, no matter how hard you try, write them explicitly in terms of y. So solving for y here, I'm going to get cosine x times sine y equal 1 is the same thing as saying the sine of y is 1 over cosine x. And so that'll imply that y is the sine inverse of 1 over cosine, but 1 over cosine is the same thing as secant. So if y is the sine inverse of secant, then dy dx, the derivative we calculated in step 2, can be expressed as tangent x times the tangent y, but y is this. So it would be the tangent of the sine inverse of secant x. And so that would be our final answer in this case. So that's a very complicated looking derivative, but the fact that we can find the derivative at all is really quite an accomplishment here, given that this is not a function and we wouldn't expect to easily be able to find the tangent lines along such a curve. So implicit differentiation is incredibly important because it's not always a given that we can explicitly write a function. Some functions we have no choice but to approach them implicitly, in which case a lot of times they turn out not to be functions at all. And so I just want you to keep this in the back of your head. This is really just an application of chain rule. That's all this is. There's nothing going on here that's special other than we regard y as a function of x and perform chain rule. So that's the main idea behind implicit differentiation. All right, thank you for watching.